Hello world, welcome to the jcore design walkthrough. So I'm Rob Landley. I've spoken here a bunch of times before. I used to do BusyBox back in the dawn of time. These days I do Toybox, Aboriginal Linux, stuff like that. This is Jeff Dionne. He created UC Linux a long time ago and moved to Japan in 2003, handed that project off to other people after it did what it said on the tin. Most of it went upstream. And these days he has become a CEO of hardware company.
I'm sorry about that.
He came down with a bit of a case of CEO and has been doing really cool things that we're here to tell you about. So, first question is, if you ask yourself, what parts of a Linux system are under your control? Your modern laptops have more ARM and MIPS processors than x86. This MacBook probably has a dozen processors in it other than the CPU. And we've been seeing a lot of things like the bad USB exploit, where you plug in a USB drive that reprograms the controller in USB. Here's an example of somebody running arbitrary code on a hard drive controller that can filter the data coming in and out of the thing for you.
So this goes to our motivation for what we set out to do here. And we thought we'd spend a couple of minutes talking about why we did this before we get into some code walkthrough of what's there in the code base and how you would actually use it and what it looks like when you run it. This is part of the motivation, if you want to go back up one slide. Okay. But there's another part too. The company that we founded and that produces this open source project uses the code to build a system on chip for very secure applications in infrastructure. So what we do is actually chips that go into things like smart grid, and not energy meters, but transmission and distribution. So this is critical infrastructure, and it's important that things like exploits are not possible there. So in order to do that, you have to have control of the platform all the way down to the code at the bottom layers. And at the same time, a little company can't afford to license cores from everybody under the sun. And so we decided, okay, well, let's start with a blank slate and spend the money that we would normally have to spend to license those cores and build a platform that we could use to do this again and again, and at the same time make sure that nobody has to do it again. And so those are our motivations for that.
Yeah. So the first question is, we want this to run Linux. What is the minimum system that can run Linux? You need a processor, some sort of I/O device, a clock to drive the scheduler, or a programmable timer to drive the scheduler, some memory for your program to live in, and some storage to load your program from.
So in about 2000, this problem became a lot simpler. Most systems are fast enough to run Linux. They have enough memory to run Linux. Back in the early 90s, when we started with no-MMU systems, running Linux in an embedded system was one of those things that people thought was a crazy idea. Why would you do that? And so we set out to prove that you could, and at the same time, we had some projects that needed the TCP/IP stack. So you got two choices, right? And you can either write or steal a TCP/IP stack from BSD or something like that, or you can port Linux to it. At least that was what I thought were the choices. At the time, people thought the choices were you license something from somebody. But we got over that particular hump, and we learned a lot about what it takes to run Linux, and this is what it is.
Yeah. So you need a processor, you need minimum amount of memory, you need the storage, you need some kind of I/O, you need a timer interrupt. You don't actually need video, audio, a keyboard, USB. You don't even need a memory management unit. You can make for your first target, you can have a very simple system, which Jeff knew about because he'd done this before. So what we decided to do is, oh, I really can't read. I got to read it up here.
Yeah, can read it down here on these. These are good.
Awesome.
Yeah, that's what they're for.
So we took a processor on which the patents were expiring, the Super H architecture, and we did a clean room clone of it with some Canadian engineers. It's called jcore rather than Super H, with the first one being J2 rather than SH2, because the trademarks haven't expired. The source is VHDL using a programming model developed by the European Space Agency that is a lot more like software development than conventional hardware development. We'll get to that in a bit. And we put together a system-on-chip build system that we need to add menu config to it because it's gotten enough options that you say, how many processors do I want? How many serial ports do I want? You know, how many peripherals? How many, you know, DSPs and stuff? And connect them all together, and it can spit out 4 different types of output. It can make a bit stream you can run on FPGAs. It can make GHDL simulator code that gives you a cycle-accurate simulator that on our most fire-breathing system can actually boot Linux to a shell prompt in about half an hour. Cycle accurate means slow. QEMU does run this stuff. We've got our user space booting under QEMU. We need to modify QEMU to actually be able to boot our kernel images verbatim. We need to describe the board, but that's a to-do item. So those 2 outputs. Third output is an ASIC mask you can use to make real hardware. You can send it to a fab and actually get chips back. Send it to a fab and a lot of money and actually get chips back. And the 4th kind is it can produce the data sheets and stuff from the source code. So this build system does all of that, and the second half of this talk is going to walk you through the code and the build system and stuff.
So an existing architecture is not necessarily what people would start with. Everybody probably knows about OpenRISC. They tried very hard to make the open source platform that people were going to use. They got quite far down the road. There were a few things in the SH architecture that were attractive to us. We started off with Leon Spark. We started doing that in the early 2000s. We got all the way down the road to the point where the chip was ready to tape out. So the GDS files were cut, but we didn't spend the money to actually do the masks. There were business reasons for that, but they weren't very good ones at the time. When you do very low-level hardware, like what we're talking about, you have a certain set of constraints that you want, right? So we're not talking about a system that has multiple DIMMs for memory in it and 64-bit wide buses and all that stuff. You want a single DRAM chip because now you're talking about the cost of a few cents instead of the cost of a few $100s. You want something that's going to be fast enough to execute what you're after, but not necessarily server-class hardware. So that sort of places us right now where we are. And it has to be meeting the requirements that we just talked about for 32-bit programming model, GCC support. Hopefully it has existing compilers because you don't necessarily want to do that. And so we started with this. And the next slide, I think.
Yeah. The thing about Leon Spark is it spent all of its time waiting for the memory bus if you gave it a low-end memory bus. We couldn't make the chip faster because it was already twiddling its thumbs on a bottleneck. So we went back and we looked at, if code density is our problem, what is the code density of the various architectures Linux already supports? Because we didn't have the engineering bandwidth to do a fresh kernel port, a fresh compiler port, porting GDB, porting strace, getting this entire software ecosystem set up. Right. We wanted something that Linux already ran.
So SH3 on this chart here is a placeholder. It should really say SH Compact, which is what the architecture actually is. Our implementation is sort of SH2 plus. And as you can see, code density is pretty good here. I think x86 64 and 386 and those are a little bit better because they have larger mind share on the compiler level. I don't think it's actually an architectural advantage, to be honest.
Even if it was, you don't want to clone a CISC nightmare.
So the SH architecture had a couple of different things about it that were very important. The first of which is instructions are fixed length. And that's important if you're trying to make very, very small hardware. You don't want these instruction decoders that are difficult to they have a big finite state machine in them to deal with taking unaligned instructions and reassembling them and all of that stuff.
These were the original ideas behind doing RISC in the first place.
Exactly. And so SH took an approach that everybody else was scared to do, MIPS and ARM and all those guys. It's a 16-bit instruction. So not only is the code density very high, and each instruction is very CISC-like, because it came from the 68,000 space. There was some collaboration between Hitachi and Motorola at the time. But this RISC concept was folded in and incorporated into it. So the pipeline becomes very simple. You load one 32-bit word every 2 clock cycles, and away you go. You have an SMP system. You load one 32-bit word every single clock cycle. If you have cache controllers in the way, you might get 10% bus utilization on the outside. That's pretty good. It leaves a lot of DDR memory bandwidth for other things. So this is an important point when you look at what are the metrics for a processor at this level, right? There are other ones. You can say, okay, I'd like to do multi-issue, I'd like to do branch prediction, I'd like to do more things in an instruction, but it doesn't really matter when the processor is this small. The only thing that matters is can I get the instructions to the processor, and what can I do with a memory bus on the outside.
And another thing, branch prediction, speculative execution, and register renaming and all that kind of stuff give you performance at the expense of power consumption. If you do work that you wind up throwing away, you drain your battery fast, you generate extra heat. So there's trade-offs all over the place. We found a sweet spot.
So keep in mind, we just want to give you a background as to why we did it the way we did it, and then we can take a look at what's in there. And this is one of the main reasons, patent expiration. So if you set out to make semiconductors, somebody will come after you. It's for sure the case that somebody has a patent on anything you can think of in this space. And so we talked to the RISC-V guys, and they gave us some very good advice. They said, make sure that not only are you patent clean, but that you can point to an implementation that is so close to what you've done that there's no way there's a patent between there and you. And I thought that was just a very fantastic piece of insight. And so we looked at all the patents around the SH2. We looked at what it was used for, and it turns out that the architects of SH are friends of ours too, which actually didn't factor into the decision-making process.
Fringe benefit of living in Japan.
Yeah, sort of that's sort of the case. But it's for sure that the SH patents have expired, and there's no way that they can come after us because we're basically a direct clone with some new instructions.
The SH2 patents, we're sure, have expired. The SH4 patents expire later this year.
And the SMP side, instead of using the SH4 approach to that, we directly took the System 390 approach or the System 360 approach from IBM.
Those patents have really expired.
Really expired. Go ahead. So this is what a typical 5-stage RISC pipeline looks like. There's the addition of a MAC block at the bottom, and there's a microcode block off of the decode stage. So it's important to look at this now so that we have something to fall back on when we talk actually about the code. Whoops, sorry, you want to go back up? Yeah. The prefetch buffer is an important part of any processor that runs something as complex as Linux. If the memory size is large enough that you have latency there, you have to get instructions into something so that you can continue to feed that pipeline. In this particular implementation here, there's a prefetch buffer. You can replace that with a cache. There are both implementations in the open source release. The one that we're showing you today is full Harvard. It has caches for I and D. And the program counter is actually not where it's shown there, but conceptually you can think of it that way. The most difficult part of something like a Super H design is the same as the most difficult part of an x86 design. It's the instruction decoder. And it's very interesting when you look at the instruction set. Most of the instructions are single cycle, so you would think, okay, I just decode it and away I go and have a single line that says this is the instruction and I do it. But there are complex instructions in here that take multiple cycles. And so there are microcode pages. And there are 3 implementations in the source code for the microcode. There's random logic, which works very well in an ASIC. We have a little ROM that maps lovely to FPGA primitives. And there's a reverse table, which is kind of like a big set of case statements. And this is the bottleneck for the speed of this particular device. So if you wanted to take this pipeline and make it faster, you would split decode into 2 stages, and you'd split execute into 2 stages, and it'd be 7-stage pipeline. And you can easily do that. And that's basically what J4 is going to look like. The ALU in this design is fairly simple. It uses a bunch of different tricks, and we'll show you what that means later. But what's missing from this diagram, because it's hard to put on there, is the register file. And the original SH register file, like in any complex design, was a full custom block in the ASIC. It had multiple write ports and multiple read ports. That doesn't map very well when you're trying to do something on the cheap. FPGAs, you can do it. It uses a lot of gate space. In this particular case, we modified three instructions to take one extra clock cycle because they wrote back two things to the register file. And everything else is writing one thing to the register file. And it's just a question of making sure that you get all the pipeline hazards right. And that gets done in the microcode. So when you look at this for SH2 versus J2, there's one or two extra clocks in a few of the instructions as a result of doing that. But it drastically simplifies the logic of the processor. And it makes it practical to implement.
Next slide.
On the memory side, the original SH2 had one instruction bus. That was an architectural mistake. It makes things pretty nasty. But maybe when we get into the instruction set, if there's time, I'll show you why they did that.
We run the same software. We're not necessarily the same implementation. We fixed some stuff. I believe you can do unaligned access with us that you couldn't in the original, for example.
Right. The DSP and MAC block in here is essentially a separate coprocessor. The J2 adds 4 coprocessor ports, which are not in the open source release, actually, not yet. They will be in a future one. You can do things like crypto accelerators. This is very important. You can do like IDCT if you're trying to do decoding of media. And those processors are easy to add to the side of the core. And the instruction expander and decoder takes care of doing that for you. And your code can be as small as a few hundred gates to add that.
Real quick,
Yeah.
an aside. When he says something's not in the open source release yet, so far we've been developing this in-house and doing
Right.
occasional tarball releases of BSD licensed source code, but we are switching to, we did our internal development in Mercurial with a bunch of nested subrepos, so it doesn't easily convert to a unified Git repository. I'm writing Python scripts to do that. There's no existing tools for this. But as soon as we get the source up on GitHub with the full history back to 2012, we're going to change our internal processes so our in-house stuff is subrepos under that, and the Git repository is the live one that we dog food. We're switching to that now. I'm the bottleneck on that, converting the repo.
Yeah, it's interesting when you do this kind of thing. The company is venture capital backed, and doing all your development in the open is not something the venture capital people understand. So,
but Jeff knows it's important.
Yeah, so at least we won't give you abandonware, and we won't dump a great big pile of garbage on you. But at the same time, the history is important, and it is there.
Yes, we know that tarball snapshots are not enough. You need the full repository history to see why we did everything we did. And this talk is to let you start out and give you somewhere to sink your teeth in the code.
Okay, so let's have a look at some real implementations. The one on the right is a fairly modern Kintex 7 FPGA. Each of the light blue cells is an occupied site on the FPGA. And this device is not, their tools are awful. It splatters everything all over the place. If you want to optimize this, you actually have to constrain the blocks, but you get good synthesis results anyway, and nobody ever looks at it except in talks like this. So
yeah, a point about that is the shorter your wire is, the faster the signal can go down it, so the faster you can clock it. So you want your bits to be as close together as possible.
So on the right-hand side of that particular diagram is a bunch of our proprietary peripherals that don't mean anything in the open source. They're essentially things like GPS receivers and analog to digital interfaces, DSP hardware accelerators, and stuff like that. And on the left-hand side of this diagram, where all those wires are connected, is the DDR controller.
The green wires.
The green. There's actually a purple box around the DDR controller up there.
Yeah.
And the CPU cores, there's dual-core CPU on that one, and it's clustered there. And on this chip, there are 2 DSPs also, in addition to a bunch of different hardware accelerator cores. And you can see that this is mostly empty. If we sort of did a push of all those cells up into the center of the chip, probably there's only 30% of that chip used. So you could put 4 cores on there. You could put 16 DSPs, and we routinely do. You can put GPU. You can put anything you want. And that chip, unfortunately, is around $150. But on this side, over here, is an $11 FPGA. And this is a uniprocessor with DDR controller and an Ethernet controller on it. So this is a practical choice if you're trying to build some kind of IoT device. You can do anything you need to do for processing, but you can't put a DSP. And in between, there's a bunch of different,
Let me give a little more context for that. When we're talking about the DDR controller, most of these FPGA development boards come with a DDR controller chip on them that we're not using. And the reason is, when you make an ASIC version of this, you won't have that. You want it all integrated on the SoC.
Right.
So we had to re-implement some of the things that these things provide as little tiny ROMs around the edge of the chip, or as little tiny chips around the edge of the FPGA. You can get the size down by using the resources that are on the board, but that doesn't help you make your own actual chip.
Yeah, so one of the fundamental principles for our company is not to license any cores from anywhere. You can do it once, and you pay the license fee, and then you get stuck, and someone says, I need a derivative, and you go pay again. And the vendor is all too happy to take your money a second time. And that just doesn't work all that well. So we do all of our own IP cores. And one of my main jobs is to make sure the investors are happy with that.
Yeah. When he says that this is a $15 FPGA chip, that's if you're going to be shipping a device with an FPGA chip on it.
Right.
A development board built around this, the cheapest we found is the Numato Mimus V2, which is $49.95 from a company in India, plus shipping. But that, we have a future slide on that, but that doesn't have Ethernet on it. That doesn't have enough gates to let you do an SMP implementation, only single processor. There's, that's a great intro chip, that's a great intro board, but you're going to outgrow it. So we have more things that we're showing about. Next slide.
Yeah. So it's neither here nor there, right? But this is sort of a roadmap that people ask us about. Right now we're in sort of in the middle of 2015. The chip that we're shipping commercially has this DSP array on board, and the faster ones are coming. Yeah. You kind of got to blow through some of these here.
So that board on the left is the Numato board I was telling about. That's
Right.
what we gave away a bunch of at our table yesterday. The board on the right is our next expansion board, the next step up from that. Once you've played around with this for a while and you find it limiting, then we have the Turtle board, which we're putting together, and we're going to be doing a Kickstarter to produce Turtle boards. Those have an FPGA with 3 times the capacity, so you can do a two-way SMP and a couple of DSPs and have a lot more peripherals. And it has the form factor of, I believe, a Raspberry Pi 2B with all the I/O connectors of a Raspberry Pi routed to the FPGA. So we will need an FPGA implementation of HDMI. We will need an FPGA USB 1.1 controller. You can't easily do USB 2.0 in an FPGA, but we can. There's tricks we're pulling. Bunch of GPIO pins, Ethernet. That has Ethernet. Ethernet opens a world of things you can do. It's a really nice board, and we will link the Kickstarter from the jcore.org website when it goes live.
So not only the Gerber files will be open, but the schematics as well. And if you want to build those boards, please have at it. It's not something we are really interested in selling. As a matter of fact, it's kind of a distraction for what we do, but we think that the open source community needs something like this. And so we spent a little bit of time to do that. The Kickstarter is a good way to get your hands on physical copies of it.
Yeah, one of the things about this is that Moore's Law is slowing down. It hasn't stopped, but it's been slowing down for a while. And at a certain point, if your hardware advances are no longer free, then you have to make more intelligent use of the transistor budget you have. And unleashing open source on that is the obvious way to keep having improvements after die shrinks don't cut it anymore.
There are many, many fabs that are underutilized at the older process nodes, for instance.
Yeah,
if you can put something useful in them. Yeah.
I see that there is the USB port, the USB client.
4 of them.
Right.
It may be used to only power the board, or I may also implement the USB device.
So the one down here,
Bottom left?
the bottom left is the console, if you want it, or you can use it as USB UART. And the ones that are normally host are also host. There's a USB hub on board, and the FPGA implements USB 1.1. So
But it's the host mode, and I'm talking about the device mode.
device mode is not implemented.
Okay,
Yeah.
thanks.
Okay, let's. Yeah, so here's sort of if you will, a rehash of the things that we're talking about. The process node that we chose for our SoC is 152 nanometer. It's actually 180, with a die shrink of 85%. That's a really old process. And it's really cheap.
Circa 1991.
91. It's a very, very inexpensive process. You can build, you can make masks at that node for about $25,000. So it becomes one of those things that a Kickstarter can do, a concerted effort of a bunch of different people getting together could say, okay, I'd like to fab that.
Can I walk them through the numbers we ran?
No.
Okay.
Yeah. And the best news on that front is it puts in the hands of the community the ability to do this kind of stuff for real projects that might have an effect on things like the tera sensor network, the trillion sensor network, right? And you can put a TCP/IP stack on a chip that costs you 3.5 cents. It's really quite interesting.
Next slide.
Yeah. And here's the economics of it. And this slide's from Xilinx, and so there are no numbers because they don't want you to think about the actual numbers, right? But basically what this slide says is the NRE for ASICs is pretty high, and you should use our FPGAs. But we've just talked about $25,000 for masks, so maybe it isn't true. The question becomes, what's your MOQ? What's your minimum order quantity for those chips? Yeah. And one wafer in 6-inch, or 8-inch wafers, which 180 nanometer usually is, you can probably put about 3,500 chips on. And that wafer is $1,800. So that's not too bad. And you probably need to buy a boat of wafers, which is 12 or 18.
Translating for the software developers in the audience, what the question this slide answers is how many boards do you have to ship before it becomes cheaper to make ASICs than to put an FPGA on each one? Because the entry cost of FPGAs is very low. There's a big upfront cost to running a batch of chips, but at a certain point, it becomes cheaper to run the chips. And that point isn't that high.
Maybe we can blow through some of the remaining slides here. So this is VHDL. There are reasons for that. It's not a question of religion. There are actual real reasons why we chose that language, and we'll talk about those.
Next slide.
Yep. And these two things are not the same. So you cannot directly translate Verilog to VHDL and vice versa. You could take a Verilog design and make a netlist in VHDL, and it will be fine. You could do the other way around. But you can't take a VHDL design that's written at a high level and turn it directly into a one-for-one equivalent in Verilog. The Verilog is not a rich language. Now, system Verilog may be closer, but VHDL is not a net listing language. So the design methodology that we used for this is called the two-process method. And when you look at the two-process method, it makes an awful lot of sense if you're used to doing software programming. It actually is different than, okay, I need a latch, so I'm going to put an always loop in Verilog there, and in there's a process for that, and a process for this, and a process for that. Our CPU probably has 3 processes in total. And they're very complex processes, but it's different. So let's go along. And avoiding common errors, we have a preprocessor tool that does that for us. So you can't write, for instance, latches in VHM, which is sort of a dialect of VHDL. It's hard to make the mistakes that you would normally make. Forgetting to connect, for instance, reset, or forgetting to pre-initialize things. The preprocessor does that. And this is sort of one of the things that makes jcore really different than something like OpenRISC or something like Leon. A lot of it is auto-generated, and it's designed to produce outputs for various different things. So there's FPGA synthesis, there's verification flows, there's ASIC flows, and the tools are all built into the source. So the RTL itself is very small, but the actual deliverable files are pretty large. And in there are things that pre-process, there are things that generate docs, there are things that generate headers. There will soon be things that generate directly device tree, for instance. So that when you make your SoC, all of this comes out, and it's all automatic.
FPGAs are great because you can boot your system at about 50 megahertz and build it and see the changes immediately. GHDL, the simulator, is great because you can stick printfs in your hardware, which is awesome for software developers.
So here, for instance, is one of the inputs, and I'm highlighting here around the CAS instruction. The CAS instruction is from System 360.
This is an open office spreadsheet that
Right.
contains the list of instructions and operating codes and stuff.
So CAS is a new instruction for jcore. It's not an SH instruction, and what it does is it lets us do compare and swap for SMP and for threading directly in the hardware. And of course, it's out of patent, which is a good thing. And the operation field here is a description that ends up in the datasheet. And the next one over is the control for X-bus multiplexer. And the next one over is the control for Y-bus multiplexer. And the spreadsheet has multiple different layers. And the output of this spreadsheet, after it's pre-processed, is the RTL for all those things I was talking about, for the microcode ROM, if you want to do it that way, for the instruction decoder random logic, for the table, and for the reverse instruction decoder, and also for the simulator.
We have infrastructure that parses a spreadsheet and produces Verilog, or produces VHDL code.
So if you want, for instance, to add another instruction, you have to find a place in the instruction table that's empty, and you put the encoding here in the opcode map, and you put the instruction there, and then you set the different fields, and away you go. Your hardware automatically does what it has to do.
Just rerun the build.
So what can you do with it now? Well, we'll show you a couple of things. You can download a bitstream and you can install it. You can build a bitstream. I think, Rich, the stuff is upstreamed, or we still have some to go. You can build Linux. Yeah.
That's Rich Felker. He's both the muscle libc maintainer and he's also the arch sh maintainer in the kernel. We have a contract with the Linux kernel maintainer. Our stuff is going to be really well supported upstream.
Right. Okay. So we'll show you some of that. And now I thought we would go through a couple of different things. So a fairly simple example, there are two things we'll do there. First is simulation. So we'll simulate a code example using GHDL, and then we use Yosis, and we'll put it on an ICE40. Then the second thing we'll do is we'll have a look at the SOC generator input spreadsheet a little bit more carefully, and we'll look at the CPU core's code organization, and then we'll run a simulation of the RTL. So maybe we'll bounce out of the slides here for a minute. And I'm not exactly sure whether I'm... Yes, I am. What do you know? So the first thing I wanted to do was to have a look at what VHDL looks like as opposed to Verilog. A lot of people in the room have probably seen Verilog. Maybe fewer have seen this. Generally, we don't use very low-level constructs in our code. We use very high-level constructs. Constants are not something that's all that interesting, but subtypes are. sfixed, for instance, this is a DSP. This is the main package for a DSP that will open source fairly soon. sfixed is a fixed point type, and the IEEE libraries will generate all of the code that you need in order to do fixed point DSP stuff right in line for you. And you think, well, what a mess is that going to make? And it turns out that it doesn't. It looks pretty good when you actually look at the gates. So what we tend to do is build things that are very, very object-oriented looking. For instance, we encapsulate not only the types into subtypes, but then we put those into records. And you can do an assignment across a multiplexer, and it does all of these things all by itself. And the code that you end up with is very small. The RTL is very small. And it's easy to understand. And it's also easy to maintain. This is a big example. Maybe we can look at a smaller one. Here's an LED blinker. And again, we organize our code in...
Blinking an LED is the hello world of hardware programming.
Right. So this is like a header file here. And what it does is it specifies the types and the components and all of that stuff for this particular thing. And in this particular case here, the register that or the record that we've specified contains the prescaler because the clock is too fast, otherwise you won't see it. The actual count is 4 LEDs, and we have a 5th LED here that's going to kind of blip, and the output record. And this type is manipulated inside the RTL instead of individual wires. And so it feels very high level, and it's easy to operate on. And we make heavy use of functions. You can also do that in Verilog, but you also get function overloading, for instance, in VHDL, which we also make heavy use of. So let's go ahead and make a simulation of that. So here we have a simulation binary that was built of the test bench for this. And it's very simple open source tools. It's called GHDL. And unfortunately, it's kind of hard to build. We'll give you some instructions on how to do that. It's written in Ada, so it's kind of unfortunate. But nonetheless, it's one of the most compliant, language reference manual compliant simulators around. And we can just run this simulation binary and have it generate a wave file for us. And so we got 50 microseconds of waveforms that were recorded into the wave file.
What he means by waveforms, he'll show it, but it recorded what the values on all the wires were, and it shows you a graph of when they changed at each timestamp.
Right. And here's what it looks like. So our count variable is changing. This one hasn't been assigned yet. That's a bug in my software. And the outputs are here. And it's fairly easy to see that
bug in your
these
hardware.
records here are containing all the different pieces. And these are high-level constructs. They're not individual wires. So if there was a state variable, there isn't in this particular case, you would see the state changing in human-readable form instead of just a set of numbers.
What he means by that, there's a stage called elaboration where it turns higher-level constructs into lower-level constructs. It's sort of like an optimizer in a compiler. So if you have a value 1, 2, 3, 4, or 5 that's on this wire, it's up to the compiler to figure out how to represent that as a voltage if you didn't give it a binding to say this is that, because we're talking to a serial port and it has to be these. Internally, it can implement that as a bus of multiple wires if it wants to. It can implement that as multiple voltage levels. It can implement that as a serial encoding. It can implement it a bunch of different ways, and you don't have to care.
So I can run a synthesis of this, but I don't think I brought an iStick board. But this is very important. It's important to have open source tools. All of the large FPGAs we were talking about are Xilinx tools. And unfortunately, here it is.
She has the stick.
Unfortunately, jcore doesn't quite fit in the largest ICE40. So we're kind of hoping that somebody does the reverse engineering on the Xilinx.
Yeah.
Right
now what we're using is the compiler for the big FPGAs from this company is a free download from their website,
right,
but it's closed source. The compiler for these small FPGAs from the other company, we can do an open source toolchain, although we got to mix and match bits from various things and need a little Python glue in the middle. But the complete open source toolchain targets FPGAs that are too small to run this chip. It's like there's work to do.
So let's make a synthesis and program the actual,
So now it's making an FPGA bit stream from the same source. The simulator code was made from this source. Now we're compiling for a different target.
And I'm going to tip this up, and there you go. So this is part of this is exactly identical to what you can see from the author of these tools on his YouTube channel. The only difference here is our build system is being used to make it instead of the scripts that come with that. And so it's interchangeable. Those scripts that build system that we have can also make an ASIC. It can also build jcore. So we'll move over there now and have a look at that. So here is a system on chip top level for our proprietary stuff. And in here, we have a bunch of different things. This is the boot ROM. This is a components directory, and we'll go there.
Our proprietary stuff is in here, but the layout of the build system
Is the same.
Our proprietary stuff is subdirectories under here.
And the most important thing from a jcore point of view is the CPU. But we also have, for instance, the caches. And there's the DDR controller, the DMA engine, and all of that. So this is a mix of the open and the closed.
We have two different UART implementations. UART Lite is tiny. UART 16550A is existing code we got from somewhere else that hasn't been cleaned up into this proper object-oriented VHDL format, but it worked before we did UART Lite.
So we were talking about code generators and system-on-chip generators. So if we look at the MIMES, which is the small board, there's a file in here called design.edn. And this is the file that tells you what it is out of that big list of IP cores get pulled in. And this is processed by our tool. And the result is a wrapper that goes around the entire chip and gives you your system-on-chip RTL, your integration, essentially. You also can get out of this the data sheet for the chip. The thing that's missing right now is device tree. Once that's integrated, it will be very simple. You just add another UART in the device tree, just drop it on the board, and away you go. And you can see that it's not very difficult to do this stuff. You essentially just drop in here, I want a cache controller, and here's where it connects internally. I want some LEDs, and this is where I drop them, and they're controlled by class GPIO. And so from this, the processing of this is very simple string manipulation to get to device tree. It's very simple to see how this becomes all the multiplexers and decoders that are required for the device itself. And this is the output from there. So here's your address decoders, for instance. Here's your CPU being instantiated. Here's your PIOs being instantiated. And if we look at soc.vhd, this is the top level where all the pins are connected. So those tools are really what differentiates this from just a CPU that you might want to put in something. So the next step from there is how to look at the CPU itself. It comes in a bunch of different directories. Most of them are not RTL code. The RTL for the package at the top level essentially just specifies the outward-facing interface. The instruction input record, the data output records, and the input records, the debug interface, so you can step and break, and there's a GDB interface for the CPU that you can use for that. And then the CPU instantiation itself doesn't contain a whole pile of different things. It's just all the different ins and outs in these records, the way that they look like that.
So yeah, this is a programming language.
Shall we ask anybody
Anybody got questions so far?
the right level or the wrong level of information? Okay.
Looks like right level so far.
Okay.
We are attempting to recruit C developers into doing this. The thing is, hardware developers tend to want to connect wires together, and they think about what the hardware is actually doing, which is the output of the optimizer, that this abstracts away a lot of that stuff that you don't have to care about, but you still have to care about some of it. The software guys don't know the things like, you know, you have to do the layout right or you can't clock it very fast. So we need overlapping information from both sides, but open source developers already know how to do open source projects. It's probably easier to teach open source C developers how to do hardware and understand layout constraints and all that kind of stuff than it is to teach Verilog programmers to do clean programming when they go, oh, I tried VHDL once, it wasn't any better than my Verilog. See, it's like the equivalent of an assembly programmer going, see, it didn't save me any effort whatsoever. I was writing assembly in C and it looked just like assembly. Well, yes, it would.
Maybe that's a little strong, but anyway. So the organization of the CPU core itself is pretty much just as described in that pipeline diagram that we were looking at. The difference between this and a lot of other ones that you might find on the internet or have written yourself if you're doing open course is we tend to keep things in a collection of functions. Earlier we were talking about the different types, right? So for instance, here is an abstract type that we use to represent what the ALU is supposed to do with its output into the barrel shifter. And so you can see that there are a bunch of different essentially
It's an enum
enums here that are used for that. And then at the end of the day, most of the things that do anything inside the CPU are functions. So here's the arithmetic unit, for instance, and here's the logic unit. And of course, you can do things like asserts, and it come out in the simulation. But when you actually do the synthesis, it goes away. And it's easy to see: case, function. If not, then blah 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 blah. Update the status register, for instance, is a function. And everything that the CPU would need to do is probably contained within this file or in one of those other ones. But they're easy to understand, except for things like the barrel shifter, which is pretty. The barrel shifter needed to be very compact, and so the implementation is a little bit difficult to understand.
That was a feature we backported from SH3 to SH2? Or from
The
J3
barrel
to-
shifter, there was a bunch of research papers that we looked at, and sort of a combination of a few of them. It's a left shifter, but anyway, it does a lot of really interesting things.
As patents expire, we do add more features. It's just SH2 shipped an awful lot of units. SH4 shipped an awful lot of units. SH3 was overshadowed by SH4 after about a year. It didn't have a long life.
The DSP extensions are contained in two files. The multiplier package, this is essentially the coprocessor for 32, 64-bit fixed point hardware extension. It has a bunch of different instructions that it executes off to the side of the pipeline. And the implementation here is very compact, and again uses parts of the thing. So you can see as you go down, it's fairly well commented. But this is optional. You can tie off all these inputs, and then those instructions become NOPs if you want, and a lot of the hardware goes away. The actual pipeline of the processor itself is contained in datapath.vhm. And the data path is necessarily somewhat complex, containing all the functions that we talked about. Where's that ALU? There. So this is the actual hardware for the ALU. And this is the logic here. So there's not much that you need to change in here. It's a fairly standard 5-stage pipeline. Once you know that the function implements the ALU, you just go look at that particular function, and away you go. So the size of the CPU itself is pretty big, but the actual size of the core itself is really tiny. There's almost nothing here. The decoder itself, we were talking about, reads from, where is this generator? Reads from this OpenOffice document. This is the actual source code of the instruction decoder. So every instruction is listed here, and across this way are the control lines. You can add more if you like. Be careful, there's some optimization in the number of them simply to fit in things like microcode ROMs, but you know, if you don't care too much about that, then it's okay. And if you look at this instruction, it's 3 steps, for instance. It takes 3 clock cycles. They're all the same, and this is what it happens to do. It takes Rn, multiplies by Rm, adds the contents of the MAC register, and writes it back. And so this is one of those ones that takes a little bit longer than we would have wanted. XBus is Rm and Rn, and then eventually over here, the MAC is going to say, I need to write back from the MAC. So not that difficult to understand how it works. And then once the generator is run, and it's that's an entire other topic. That particular tool is included in the source code, but it has it's written in Cloture, so you need Java and a bunch of other things in order to run that. You get the multiple.
We ship the generated files, so you don't have to install that until you're ready to open that can of worms.
Right. There's the decoder itself in table format, just as a ROM. So this is a real microcode ROM. There's another version of that that's simple. And this one is, of course, just RTL. And this works very well for ASIC. It turns out that the logic is very compressible. And so when we synthesize for TSMC standard cells, it comes out to very, very small. It's not pretty good, not that good for FPGA. And just a forward running table that you can also use. What did we say we were going to talk about? Oh, yeah.
Do we have questions at this point? Okay. Hang on, microphone coming.
That Numato board is available through Amazon,
Right.
and it's $70. They have it in stock.
$49.95 from the original website.
But
So if you don't mind waiting for it to be shipped from India, it's $20 cheaper.
So the same scripts that we used for the simple LED blinker here target the Xilinx toolchain, and we could just type a make at the top level and we get a bit stream that contains the MIMUS v2, but it takes 35 minutes to run. So instead, what we'll do is we'll make a simulator instead. And the boot ROM in here boots to a GDB stub, because why not? So let's run. CPU test bench. And if you've ever looked at the output of a GDB stub, there you go. At which point your GDB will say GDB, and you can upload a file over the emulated console port and run your code. And as Rob said, if you have half a day to wait, it'll boot Linux. So there you go. We hope you try out the jcore project. At the moment, it's a big collection of stuff, and it might seem like a lot to get your hands around and a big collection of tools, but hopefully a community will coalesce, and it will become easier and easier to do.
We've got Linux booting to a shell prompt on real hardware, so you can start with a known working environment and then break it.
So here is this one is running Toybox and BusyBox. This is an SMP system, proc. And caches. Yeah.
Yes, Rich
what,
got it working.
What's the what?
Is FDPIC working?
Yeah.
Yeah. We have both binflat and FDPIC working. Binflat with UCLibc, FDPIC with Muscle. FDPIC with Muscle is totally the future. The UCLibc one is there because we already got it working and haven't killed it.
So, and just to show you that a shell prompt is not the only thing you can do, our proprietary stuff that some of you may have seen is called Caliper.
Synchrophasers.
Synchrophasers. 192. Oops. And there you go. So here is a web server actually running on that particular board. There's nothing connected to the board right now, so you got 0 inputs. But as you can see, it's real hardware. It's not just a CPU core running in an FPGA for no particular reason. There's a purpose for this. We didn't set out to just build this. We set out to actually make things like power quality monitors, which is what this is, with stuff like FFT engines and wavelets and all of that kind of thing. Hardware accelerators that you couldn't get on off-the-shelf system on chips. Great. Any questions?
Where do you go to try
We have a website, j-core.org, that we're still fleshing out. That's where we're open sourcing all the stuff. We'll link the GitHub from there once that's up. There, we tried to set up a mailing list this morning. The old mailing list that we set up last year went down. We tried to set up a new mailing list, and it turns out nobody that we have with us is a qualified system administrator. So we're fighting with Postfix and Mailman and a few other things. So that's where we wanted the mailing list to be, and if you email to it right now, it will say that there's a circular route, and that's so much fun. But if you go to the main j-core.org webpage, you will see a whole bunch of HTML written by someone who knows paragraph tags and H1, H2, and H3. If anyone would like to donate a style sheet to us, that would be awesome. We're putting a lot of material on there. There's a lot of broken links and stuff, but we'll be filling those in over the next few days. And what I'm going to do is, as soon as we have the Git repository up, there will also be a web Git repository that has all the web stuff. And, you know, give us pull requests if you want to update the website info. Yeah, that website. I didn't hear.
It's okay.
Oh, SEI's Twitter feed. At SE Instruments. And you promised to actually update it now. Yeah. Okay. Got a lot of updates. Good.
Thanks for coming.